So I want to talk about how we're attempting to enhance enterprise cybersecurity using statistical methods and machine learning to complement the existing defenses. This is work we've done informed with and in collaboration with particularly Microsoft, Los Alamos National Lab, and I'll show you an example from their network, and parts of UK government. So this is what you don't want to see, right? You just heard really terrible, scary news. Here's an example of another sort of scary news you don't want to see. You don't want this. This is the WannaCry flash screen, right? You get that on your screen, your computer is now owned, it's ransomware, you can't unlock it easily, okay? WannaCry caused a lot of upset when it hit in 2016 because it appeared indiscriminate. It affected hospitals in particular, and that somehow was a line that shouldn't have been crossed, perhaps. In fact, it was indiscriminate only in the sense that it was seeking an exploit on unpatched computers in the world, and many hospitals had them. This is what we want to avoid. I'm guessing an audience like this will know all sorts of factoids about cybersecurity. Generally, it's considered a critical issue by the government. I don't know quite how they compute these numbers. 2016, it was 30 billion. Yeah, well, 250 million a week on the side of a bus. I don't know where these numbers come from. Just agree on that. What we're trying to do is complement existing defenses. So an enterprise typically will have a firewall, and that's the sort of main line of defense, and then each computer has a virus scanner and various other bits and bobs. The problem with that is it's all signature-based. You need to know what you're looking for so you can block it. We're trying to complement those existing defenses, not trying to remove them. We're trying to complement them with machine learning, statistical ideas to do anomaly detection. Has the behavior of this device, this person, this entity changed in a way that is both unexpected and may be indicative of a kind of malicious behavior? Now, I already know what you're thinking. I wish you would finish, but beyond that you're thinking, well, the problem with that is false positive management, and in fact, more generally than cybersecurity, the big problem of data science, which used to be called data mining, the big problem here is the bigger and bigger challenges we address, false positives are a problem you can't escape from, and so it's more a question of management. So Julie talked about trade-offs, and I think many of the talks have had a character of talking of trading one thing against another. The trade-off in security is security versus usability. The more you lock down a system, the less convenient it is to use. So it's all a trade-off in there. The data we collect, it's not like the sensor systems. This is all collected because it's being collected for other purposes. So the sort of things we collect is net flow, that comes off routers. It's not designed for security, it's designed for something else. Authentication, well, there's an authentication log. Where did you log in? Which device authenticated against it? DNS requests, which is something about the routing of IP addresses. Web proxies and cache. The thing that's become fashionable in the last couple of years is host-based analytics. So a virus scanner is a very simple host-based analytic, but one can do much more on a device in terms of data acquisition and potentially monitoring. The issue here is the conceptual granularity of the data is much lower than how we conceive of a cyber attack. What does a cyber attack look like? This is a good example. This is the only example I know in the open literature where the US government sanctioned US government employees to describe an attack that they attributed to a foreign state actor. The nodes, the points in this picture represent devices on the network. Connections represent communication events. So here's the high-level story of a cyber attack. Somebody on this computer clicked a spear phishing email. Unfortunately, their computer was vulnerable to the exploit. At that point, the attacker has a door, a back door. Well, what sophisticated attackers do, remember there's all sorts of different kinds of attack, what a sophisticated attacker wants to do is escalate their credentials. Want to
have the keys to the system, if you like. And so a very typical activity is then to find other computers that this computer has a relationship with, explore the credentials on those, and what's called laterally traversed, or in hacker speak, to pivot across the network. So in here, tried these, didn't like them, got to there, like that, tried those. Okay, this part, this was being continuously monitored. The network was being continuously monitored. This took 45 minutes. Where they were going after was in there. Okay, that's the Active Directory server, which is essentially the keys to the system, the authority of the system. But what you see in the data is this computer spoke to this other computer at this time and it transferred this many packets. So it's easy to tell stories about it, but when you look at data at low granularity, we're into another problem. Huge challenges. I'd love to say it was easy and then we can get back to trying to fix the climate change thing, but this is hard as well. Data volumes are often huge. About 140 terabytes a month on the South Kensington campus at Imperial for NetFlow alone. The data's coming fast. Again, South Kensington campus of Imperial, about 4,000 communication events per second on the routers. It's very heterogeneous. Different people do different things for good reasons and malicious reasons. There are both known temporal variations, academic terms, time of day, weekends, and unknown temporal things. Something changes about the cohort, the behavior of how people are visiting the net. A new picture of a cat appears on the internet and everyone's excited, so they all go to that site. So there are unpredictable temporal variations. There's a latent variable hidden in all this. So right now, if you've got your laptop open and you're connected to the network, even if you're not doing anything, you're not typing anything, the computer is in a continual exchange. Right? There's a continuous flow of computer-generated activity. And it's interesting to try and separate the human from the machine in terms of the data. Timeliness, it's no use to dig out a cyber attack that happened 5 years ago. Too late, damage is done. And there's a dearth of labels, so quite a lot of the discussion has been about supervised methods, and maybe I'll describe one way to do that. But mostly these things can't be labeled. A cyber attack is a coordinated sequence of activities. It's not this one communication event or this one authentication was the insult. It's the combination of things. So these things are very rarely labeled, which pushes us into unsupervised learning territory. I don't think at the moment we're in a position where we could just say, and I'm glad Murray's gone, I don't think we're in a position where we could just say, all right, I'm going to just cram all the data together somehow and feed it through a massive deep learning network and magic will pop out. The structure of the problem is too complicated. And it's not well enough understood. This is not distinguishing cats from dogs, which I think we might have reached the limit of at this point. Okay. So our view instead to actually do something now is we think about different structures in the network. So we could think about the whole graph. If the whole graph changes in a large way, well, the attack is now happening, right? They're attacking directly. We could think about subgraphs, we can think about edges, communications between me and Nick, say. We can think about the structure of a communication, so it's all packet-based activity. The idea we're working with is build analytics on these things that are designed based on what analysts tell us concerns them, and then throw anomalies. The idea then, combine those anomalies in one way or another to filter down nearly all of this data to a few things to present to an analyst. So I've just got to remember what the hell I was talking about. Right. So filter the data down, try and put the analyst, put their focus where it's needed. Something Nick said at the beginning I very much agree with, particularly in this context. I'm not fantasizing here about an AI device having full control of this. what we want is human-in-the-loop security. Okay? We inform a human expert who makes a decision. Just as I don't really imagine critical healthcare being fully AI. The machine informs the human takes responsibility. Maybe one day, but I think that's distant. Okay, so the devil is all in the detail, right? That was a few jokes, some anecdotes, a picture of a cyber attack, that's all fun. What do? So we build machine learning methods, statistical methods, and we're mostly methodologists, so we try and construct principled methods. So methods where we can make mathematical guarantees of one sort or another, like these different sorts of trade-off. How do I guarantee I'm doing a minimax solution? Particular areas of interest, change point detection, sequential or otherwise. Has the intensity of something changed? That can be indicative. The way if you go now and read about WannaCry, okay, so we now know WannaCry manifested on specific TCP ports, and if you go and look in the data that was kicking around that world at the time, you can see exactly what you'd expect, which is a peak in a specific port, a peak of activity. Of course, you don't know that in advance, and that's why we need the unsupervised learning. So we do a lot of stuff on change detection. Change and novelty are things that network analysts worry about more than anything else. But then, okay, really I'm just this nerdy stats guy, right? It's breaking my heart that I haven't got any equations for you. I feel like a fraud. So really what we do is develop the mathematical tools to do these sorts of things in all sorts of different ways for all sorts of target. And they're sort of tuned to do specific things, to handle some amount of unpredictable variation, to deal with complicated data structures. We've had lots of fun playing around with spectral methods. So Fourier methods, where we can get away with it. Beaconing. Once an attacker is in, they want to get stuff out. They probably, if they're that sort of attacker, want to do it discreetly. So very typically a malware will beacon out of the enterprise for information. So I'm still here. When you're ready, I'll send stuff. Okay, so that often manifests as a regular pulse, or they're clever and they'll say, well, it's an exponentially regular pulse, but you can still pick it out with appropriate tools. We've done one idea I like. I've called this future prediction, and I think that's a really stupid name. You don't predict the past, do you? But the idea is to say, right, if I look at your behavior through the lens of the data in the last 5 minutes, can I predict something about what you'll do in the next 5 minutes? Like, are you going to make a new are you going to establish a connection to a computer you haven't spoken to before? And you might think, no, of course, I'm me and completely random and special and unpredictable. Turns out you might be, but your computer isn't. And a whole bunch of more different sorts of methodological things. So if you look at my website, you can read endless boring papers. They were as boring for me to write as they are for you to read, trust me. But methodologically, what I think is, what one part of our work is, imagine that basic stats textbook you learned from with all the t-tests and histograms and so on and so forth. What we're trying to do is take that and reformulate all that machinery such that it will update when it sees every data point, and it will adapt to the fact the data is moving. So that's the toolkit for statistics on streaming data. I kind of want to show you this, but data fusion, very interesting, right? So this idea of, can I predict whether you'll make a new, will you connect something you haven't connected to before in the next 5 minutes? So that gives me the chance to phrase a supervised learning procedure, okay? And then I'm going to construct some features and do that any way you like. Experts would do it better than I would. Domain specialists would have more insight. And then I'm going to just use some machine learning procedures to make predictions. Did you or did you not make a new connection? Now, NetFlow is about communication. It's, I spoke to Nick at this time, and I gave him this many packets and stuff. WLS is, Is somebody logged in? How many people are logged in? Is the screen locked? And things like that. It has no explicit communication in it, right? Nothing about communication. Now, I don't know if you know how to read these sorts of pictures. This is an ROC curve. It measures how much two distributions overlap. Or it characterizes how much two distributions overlap. The nearer you are to the corner, the better you're doing, okay? The blue line is how well, and if you're on the diagonal, it means you're doing no better than guessing. The blue line is using WLS. Apparently, even using data which has no explicit communication content is still predictable of whether you'll make a new connection. What it's probably doing is capturing human aspects. And for the record, this is surprisingly good performance, and we always care about the low false positive end, right? And it turns out we've got some novel fusion methods to try and mash the data together that help. Anyway, I'm kind of running out of jokes now, and that lady's waving, what, is it 2 minutes, or is that a different gesture? Sorry. Cybersecurity is very challenging. Methodologically, it's brilliant. We have to work with people who have the real problems to do this. And I've tried to justify that it's important. I think we are amongst the leading institutions in the world at this activity right now. And one final comment, many of these ideas apply much more widely than the specific context of enterprise cyber defense. This is completely sort of consistent with the structure of what people do in plastic card fraud detection, for example. Anyway, because I didn't know, it's always hard to know how to stop. Okay. Thank you very much.